Hi everyone, I'd like to provide an update on the CoiFly electric harness project, the changes I've made since last time, and what's next. I will also answer a few common questions at the end, so stick around. If you haven't watched my previous videos, we're developing an electric propulsion system for hang gliders that lets us launch from flat ground instead of having to drive up a mountain. Last time I switched from 2 big 6S batteries to 8 small 7S batteries. This increases voltage by 16%, which reduces heat losses in the ESC, preventing it from overheating. But this also forces me to use a lower kV motor with thinner windings, so even with reduced current, I don't think there is any reduction in heat losses in the motor, which is the main source of heat losses in the system. So I think I will have to upgrade the motor. Since I'm now using different batteries, I made all new battery boxes for them, and I put the boxes one behind the other to reduce drag. Unfortunately, this proved problematic in practice. I mentioned before that for a powered harness, you want to have the center of mass as forward as possible to achieve good handling. You don't want heavy weight dangling by your feet. And so the aft placement of the second battery box makes things noticeably worse in this regard. But that's not all. When you're taking off at full power, the propeller's P factor wants to tilt your harness slightly to the side. Normally this is not a problem, but with the weight of the new battery boxes sitting so tall over the center line, when the harness is tilted sideways, the weight of those boxes shifts sideways significantly, and that can interfere with your normal weight shift input, which is not something you want to happen close to the ground. In this footage, for example, I had to briefly drop the throttle to be able to course correct. To remedy this issue, I have since moved the battery boxes closer to their original position, side by side. Then there's the manufacturing. The old battery boxes I cut and bent by hand with a few manual jigs, but the new design demands more precision than my hands can deliver, so I had to figure out how to cut them on a CNC. And cutting such a thin sheet steel is not an easy task, especially on a hobby-grade CNC. That was quite a journey. Normally, I get sheet metal parts laser cut by another company. However, for the battery boxes to keep weight reasonable, I need very thin steel, only 1/4 millimeter thick or 10 thou, which this company just doesn't offer. In fact, so far I haven't found any company that readily offers cutting, let alone bending, of such thin material. If you know of a company who could cut parts like this in small quantities, please let me know. Now to the fun part, electronics. I implemented many electronics upgrades, including digital signals with error detection and more advanced battery monitoring. Overall, it's more robust and reliable. I'm very happy with that. In principle, you could just read the value from an analog throttle sensor and send the corresponding PWM signal to the ESC. So why then do I have this pile of previous iterations of my circuit boards? Well, the short answer is safety. Are the batteries getting too hot? Are their voltages acceptable? The system should keep the pilot aware of any such problems as they develop, and in certain cases it must decide to kill or limit power on its own. This needs a lot of sensors, increasing complexity. Here's one of the PCBs I designed. You put one of these on each battery to measure its temperature as well as the individual cell voltages. The information is then reported to the main module of my system. So, I designed this board, had it manufactured in China, and then I manually soldered this black Arduino board on top. This is a nice and easy way to prototype things, but now I want to make it more robust and miniaturize it, which needs a new schematic and a new Arduino code. I wanted to hire someone to do this task for me, but nobody's been interested so far. I guess consultants have bigger fish to fry, unsurprisingly, so it's yet another thing that I have to do myself, probably. Multiply this situation by like 100 and you'll see why productionizing this project is taking so long. I also switched to a different speed controller. My previous one was overheating too quickly and also did not have an electronic brake. So I tried the VESC 75-300 and the Hobbywing Platinum 260A. Hobbywing is a typical ESC with a trapezoidal commutation, whereas VESC uses fancy sinusoidal commutation, which is supposed to be more efficient at partial throttle. But partial throttle is not really our use case, and unfortunately I'm not seeing any significant performance advantages to VESC at full throttle. According to my telemetry measurements, VESC seems to consume perhaps 10% less power than a Hobbywing for similar mechanical output in static testing. but I'm not sure if this measured difference is actually real. The motor is heating up pretty much the same amount with BESC as with Hobbywing, which means that they have similar total heat losses for similar mechanical power output, which leads me to believe that they are probably equally efficient, and my measurements of current are simply not accurate enough, or my two tests are not under equal enough conditions. What do you think? Does that make sense? My next test flight will be with Hobbywing because it is much smaller and lighter than BESC, so it's easier to physically integrate into this project, but perhaps I will try BESC again later. As soon as I added the temperature sensor to the motor, I realized that I've been running it too aggressively all this time. I think it may have reached temperatures above 100 degrees on some of my previous flights. It was just too much. I'm currently using MAD M30 80 kV motor, which is designed for drones, that is for intermittent workloads, whereas we're pushing it at full throttle for several minutes. I think the next one I will try is MAD V128. It is a bit heavier and has a larger diameter, so it should be more efficient and also able to dissipate more heat, I hope. I'm very limited by weight for the motor, because adding more weight at your feet noticeably deteriorates handling, so it's a tough trade-off. Another option is to reduce the power requirement. For example, we could settle for a lower climb rate. We have a lot less issues at 1 meter per second climb rate compared to 1.5. I could also use a more efficient propeller, which would require less power to produce the same climb rate. Currently, I'm using a carbon-wrapped wood core propeller from Engel. It is better than the others I've tried, but it's heavy and it doesn't fold, so it will cause more drag while soaring. We could get better performance from a slightly bigger and lighter carbon fiber propeller with a thinner airfoil. Sadly, as far as I can tell, they don't really exist in this size. It's too big for RC planes and too small for real airplanes and even paramotors. This is another persistent challenge in this project: lack of pre-made components in the right size. The closest thing I found is this drone propeller, which is 40 inches or 1 meter in diameter. It is very well made, is very light at only 200 grams or just half a pound, but unfortunately it is not foldable. And it also doesn't have enough pitch to be efficient at our airspeed. So my plan is to cut it in half on the CNC and make a folding hub for it that would set the blades at slightly higher pitch than they were originally. This kind of surgery is time-consuming, but will help a lot with prototyping because it lets me try different pitch angles and propeller diameters to find the most optimal one experimentally. And once I figure out what propeller size works best, I will see if anyone out there can economically design and manufacture a custom folding propeller in this size. If you have any pointers for that, please let me know. Alright, now here are some answers to a few common questions as promised. How much does it weigh? Currently, KoiFly weighs 18 kilograms or 40 pounds. This includes batteries and everything else that you attach to your regular hang gliding harness. What is the endurance like? In my tests, KoiFly has enough battery to climb approximately 500 meters or 1600 feet. From there on, you will need to rely on thermals. In fact, you should probably reduce the throttle before running out of battery to extend the time you have to find the first thermal, because of course, cruising around takes less power than climbing. Alternatively, if you don't even want to climb high and just want to cruise around at low altitude and calm weather, you can probably fly for 20-25 maybe minutes. The batteries are swappable, so you could potentially fly more than once per day. One set of batteries costs around $1,200 and takes a couple hours to recharge. How much will it cost? I can only give you a very rough idea right now. The components that go into one harness kit cost around $3,000 if purchased in small batches. This does not include the cost of batteries that I just mentioned, or any labor or profit, or it's just the base material cost. I'm still iterating on the design, including on ways to reduce manufacturing costs, so I don't know what it will look like in the end, but my goal is to make it affordable. Can you get a KoiFly harness kit right now? No. At the moment the system is still in development. I'm working on improving it and on testing the improvements. If you're interested in this project, subscribe for updates, as I will be posting more videos as I make progress. Also, check out the previous videos on this channel, including the comments, which have some more information and interesting discussions. Alright, this is it for now. Sorry for the long delay in publishing this update. I will try to post shorter but more frequent updates in the future. Have a good summer season and fly safe.